Hello everyone and welcome to today's session on Engineering Materials Lab. Today we'll be learning how to determine dielectric constant of the given sample. In this particular session, we'll be talking about the dielectric materials, the value of dielectric constant, and the origin of the dielectric properties for a given material. And we'll be rounding up this session by talking about the details of the measurement setup that we use in the lab for this particular experiment. So if we talk about materials and their properties, for the electrical properties, what we find out is that there are three types of materials. We have the conductors, which have very large conductivity. We have semiconductors, and then we have insulators. So this difference between the materials arises because of the value of the band gap for them. Conductors generally have zero band gap. Semiconductors have small band gap and insulators have very large band gap of greater than 3 electron volt. When we talk about dielectric materials, what we mean is essentially the insulating materials. And a very special properties of the insulating materials is that when we apply electric field on them, since there are no free charge carriers because of the presence of very large band gap, so no charge can flow through it. So it does not, no current flows through the system. Rather, what happens is my material becomes polarized. And because of this property of the insulators, they or dielectric materials as they are commonly called, they find extensive use for insulation as well as in capacitive applications. Capacitive applications of a dielectric material depends on its dielectric constant. And dielectric constant or relative permittivity of a material is defined as the increase in charge storing capacity by insertion of the medium or the dielectric medium between the plates of a capacitor. And this particular definition is what will be used in our setup also. The enhancement of the capacity of a parallel plate capacitor in the presence of the given dielectric material. And this enhancement of the charge storage is because my material becomes or a dielectric becomes polarized in the presence of the applied field. And always we must remember that the value of the dielectric constant is greater than 1. So if we look at the physical phenomena which gives rise to a material becoming polarized in the presence of the electric field, it is essentially the alignment of permanent or induced atomic or molecular dipole moments with an externally applied electric field. If we look at an example here, what we see is we have an atom, and in the absence of a field, the center of mass of the electron cloud and the hole lie absolutely on each other. So there is no net dipole moment. But when we apply the external electric field, the electron cloud moves itself based on the direction of the applied electric field. As a consequence, now the center of mass of the positive and negative charges no longer coincide. So my material has a net dipole moment, or we can say that it has become polarized. Similarly, we have an ionic system in which the ions, the positive and the negative ions, the anions and the cations are regularly arranged. So as a consequence, if I look at it, the net dipole moment of the system is zero. So there are charges, they are separated from each other, but the arrangement ensures that net dipole moment of the system is zero. When we apply the electric field, there is a very small amount of movement within the cations and anions. Very small, as in like picometers. This is the kind of movement we are talking about. Remember, the movement will not be so much that the ions actually are able to break the bonds. Because in that case, what we will get is, if we apply that higher field, actually we are having a dielectric breakdown. So remember, we were applying a small amount of field. As a consequence of that field, my ions are going to move by a very small amount. But that very small amount is sufficient to ensure that the net dipole moment is no longer zero, and hence my system is now polarized. In the third case, if we'll see here, the third case is of a system in which I already have molecules having permanent dipole moment. Before the application of the field, these molecules were randomly arranged. As soon as we apply electric field, what we see is that these dipole moments get aligned to the applied electric field, and my material becomes polarized. So what we are saying is, there are three types of sources for polarization: the electronic polarization, the ionic polarization, and the orientational polarization. And all dielectric materials exhibit at least one of these, depending on the material and also the manner in which the external field is applied. Now let's talk about the details of our measurement setup. Our measurement setup in the lab is based on LC circuit. So essentially we have an inductor, and serially to it we have two capacitors. We have the standard capacitor SC, and then we have the dielectric cell DC, and the whole LC setup is being uh, activated by, or it's being charged using an audio oscillator. Now what we have is, this DC essentially, or the dielectric cell essentially, consists of two gold coated brass plates within which we'll be keeping our samples. So this X is, which is my sample, is going to be placed between the two gold coated brass plates, and then that's how my measurements will be done. And remember, audio oscillator is incorporated inside the instrument, so it's inside my dielectric measurement kit. There is no separate audio oscillator required. So if we look at this, if we look at our circuit, what we find is that we have the standard capacitor SC. Across the standard capacitor, we have the voltage VSC, and the current through it is I. So we can write the impedance for this particular capacitor by this formula. So the current through the circuit can be given by I is equal to omega VSC into CSC. Now this I flows through the dielectric cell also. So for the dielectric cell also, we can write that VDC by I is given by 1 over omega C DC. So I can actually determine the value of the capacitance for the dielectric cell, which will be given by this sample. So what does this tells me? What this tells me is that by measuring the voltage across the standard cell and my dielectric cell, and using the value of standard capacitor, which is already known to me, we can actually determine the capacitance of the dielectric cell containing the sample. And afterwards, what we need, the next step that we need to do is, we need to determine the value of the capacitance of the capacitor when there is no sample. So this is the value that we arrive at. Here we need to always remember that R is in meters and D is also in meters, where R is the radius of the gold plated discs which comprise the dielectric cell, and D is the thickness of the sample. Okay, so this is very important to remember, that every sample, if it has different thickness, so we will need to find C naught for every sample separately, because the amount of air present between the plates will be different for different samples, because D is different for each sample. And once we have determined C naught using the C dc found in the earlier equation, we can determine the value of the dielectric constant. Thank you. Now we move on to the next video.